Hello, linear algebra, math 2318 students. We're in section 5.4, second example of using coordinate mappings to help analyze a linear transformation between two finite dimensional vector spaces. So in this example, we're going from V to W again, but this time V is P2. That's a set of all polynomials of degree at most 2 with its basis beta with 1 to t and t squared in it. And we're going from P2 to P3 under a transformation that the book shows you how you could prove, or you could do it yourself, why that's linear. It's a transformation that takes a polynomial of degree at most 2 over there and multiplies it by t plus 3. In general, that's over here. So it takes a polynomial p of t and just multiplies whatever p of t is by t plus 3. Well, that ups its degree, doesn't it? So the codomain is p3. And for example, t squared minus 1 comes over here, gets multiplied by t plus 3. You can multiply that out using FOIL, and you get t cubed plus 3t squared minus t minus 3. And if you're looking at P3 with its canonical basis, 1t t squared t cubed, that just picks off those coefficients as, let's see now, that should be the other way around, right? Because we're going in descending order, right? So the linear coefficient goes in first. So if I'm using the usual coordinate mapping over here from P3 to R4, I would say the first coordinate here is a minus 3 times 1 plus a minus 1 times t plus a 3 times t squared plus a 1 times t cubed, right? Okay, so the question is, what matrix could have done this for us? What could have taken minus 1, 0, 1, which is the coordinates for t squared minus 1, right? The coordinates in R3 for the polynomial t squared minus 1 would be minus 1, 0, 1, right? What matrix multiplication on the left of that would have given us this? And so that if we have this matrix, we can figure out this matrix, then we can transform anything much more quickly, just matrix multiplication versus all the algebra you and I went through here to multiply those and gather like terms, et cetera, right? When you're multiplying polynomials longer, of higher degree than 2 or 3, it could get quite complicated. Matrix multiplication could automate that quite quickly. What matrix will do the trick? Okay, so to find that matrix M, you need to find the image under the D basis, with respect to the D basis, of the images of the basis vectors here. If this is B1, B2, B3, you find their images over here and what they're referred to in terms of the coordinate mapping having to do with basis D. So we need to find these quantities. Okay. Well, that's pretty easy to do. And remember, this will automate the process for the future. So T of B1. So B1, what was it? It was the basis vector 1. We're going to multiply it by t plus 3 because that's what this linear transformation does, and we get t plus 3. T of B2, again, we take that basis vector t, multiply by t plus 3, we get t squared plus 3t. T of B3, here's B3, t of it, multiplies it by a t plus 3, gives us t cubed plus 3t squared. So you'll notice these are the images of TB1, TB2, and TB3 sitting over here now, but I don't want just them, I want their coordinates in terms of R4. So that's what this coordinate mapping with respect to the basis D has basis vectors 1, t squared, t cubed. There's 4 of them. That's why this mapping, represented by the green coordinate mapping, is going to give us vectors in R4. So if I take the coordinate mapping of t plus 3, that is 3, 1, 0, 0, right? 3 is the constant term, 1 is a linear term, 0 quadratic, 0 cubic. T of B2, that'll be 0, 3, 1, 0. T of B3, that's t cubed plus 3t squared, and that is 0 constant, 0 linear, 3 quadratic terms, and 1 cubic. You take those 3 vectors and you put them right in here. So you'll notice that the matrix that does all the work for us in general, is going to do all the work for us in general, is going to take vectors in R3 to vectors in R4. It's going from the basis beta to the basis D. This was 3-dimensional, that's 4-dimensional. What's going to do that? When you're multiplying a vector on the left by a matrix, what's going to take 3-dimensional to 4-dimensional? A 4 by 3 matrix. 4 rows, 3 columns. So, what have we found out should be in there? 3, 1, 0, 0 should be this first column. T of B2, its coordinates are 0, 3, 1, 0. And T of B2 is 0, 0, 3, 1. And yes, that's a 4 by 3, 4 rows, 3 column matrix. 4 by 3. Okay. So let's just take it for a test drive, see if it's working. So if I put that in here, 3, 1, 0, 0, 0, 3, 1, 0, 0, 0, 3, 1, and multiply it by P. What is P in terms of the basis beta? The coordinates of the vector P, which was the polynomial t squared minus 1. Its coordinates in R3 are negative 1, 0, 1. If I multiply negative 1, 0, 1 on the left by 3, 1, 0, 0, 0, 3, 1, 0, 0, 0, 3, 1, what do I get? Well, let's see. The first thing I get is a negative 3. The next thing I get is a negative 1 and 0. Then I get a 3, and then I get a 1. And that is exactly what we got the hard way by doing the linear transformation using a lot of algebra polynomials. Having this matrix will automate that process for all future questions. You should try it. Come up with some polynomial of degree at most t, find its coordinates, multiply it by the matrix, this matrix on its left, see what you get, and then compare that to going the other way, taking that polynomial, multiplying it by t plus 3, putting it in descending order, and then figuring out what its coordinates are using this coordinate mapping. Okay? Should be the same whether you go this way or that way.